All right, in this module, we're going to continue talking about sample preparation and specifically grinding and then polishing. So as I said before, grinding here is we're talking about flattening a specimen surface. So we've already cut it and mounted it. And so now we're going to make sure it's flattened, and we want to remove any damage that we cause during the sectioning process. So how this is done, and we're going to go through detail of this, but is by contact of the specimen with a series of grinding or abrasive papers. Basically think sandpaper. These grinding papers are some type of particle of a specific size, usually silicon carbide, bonded to the paper with some type of adhesive. The level of coarseness of those particles will then in turn dictate the resulting finish of the specimen. So larger size, larger scratches; smaller size particle, smaller scratches. And so you go through a progressive list of these grit sizes. And so these grit sizes are what determine the size of the particle. So we can have things like 120, 240, 320, 400, and 600 grit, etc. And so before we sort of get into this, I want to see what you know about this process and what you don't know, and see if you can tell me which will result in a smaller scratch size on a specimen. Will it be the 120 or the 600 grit? Which one will cause a smaller scratch size? And then also, what do you think that grit number actually refers to? So in the quiz, go ahead and complete those questions and then come back and we will discuss. All right, we're back and you've had a chance to answer that quiz question. So now let's take a look at the answer. So smaller scratch size on a specimen, will it result from the 120 or the 600 grit? This is going to be from the 600. So the way this works is the larger the number, the smaller the scratch size, the smaller the particle size is. So that means lower numbers are more coarse, higher numbers are finer, right? And so what these grit numbers actually refer to is the mesh number. A while back I did a demo with sieves in front of a laser. The sieves, I didn't really tell you much about their use or anything, but they're used for separating particles. And so a mesh number pertains to how big those mesh openings are. So when I have 120, 600 grit, that means that those particles on that grinding paper have passed through that grit. And so so if we think back to the one of them that I used in that demo, I used a 325, and that had an opening size of 44 or 45 microns. And so, you know, that's the mesh size. So if I see a grit number of 325 as well, and so we have a common one is 320. So that 320 may not surprise you, but the particle size of the silicon carbide is roughly 40.5 micrometers. So that tells us whatever passes through, it's the same size. So basically the grit, just this is more for your curiosity, but if you're looking at grinding papers and you see a number, that number corresponds to the sieve that we're talking about, which are frequently given mesh numbers, and those mesh numbers correspond opening sizes, and that will pretty directly relate to the particle size that you see on these grinding papers. So for the most part, what we do after sectioning, we typically start with a 220 or 320 grit. So one of those that we just talked about, that's a good starting point to remove the initial damage from sectioning. All right, so let's talk about the grinding process, not just the size of the papers. So grinding can occur by hand. So I have basically what looks like a piece of sandpaper, and I apply my sample to it that's mounted, right? So I manually move it across the sample, or across the sandpaper. There's also belts, so basically a long strip, and then I can basically rub my sample across it in a linear direction. There's also machines, and so with those machines, you typically, have a motor. So this is my motor of a sophisticated motor, and then you have a wheel on top of it that's going to spin, and you put your grit paper on top, right? So that's going to move, and then you're going to place your mounted specimen on top of it. So you apply a force down, and then the motor does the work for you, and you just hold your sample in place. So that's the most common. And there's automated versions of this assembly that can give more standard, consistent results. Typically, also there is water. So if you think about this process, there's a lot of friction. That friction causes heat, so that's an issue. So remove heat from friction, and it can also remove particles. So if some of the silicon carbide comes off, that can be removed via the water. If there's bits of metal or the mounting material that come off, the water can facilitate its removal as well. All right, so we've got a machine, we're doing it by hand. It doesn't really matter, but the idea is that we're going to start with that low number. So let's go through a typical procedure that we might do. So let's say I'm going to start at 240 grit. All right, I'm going to start there. This is going to be my specimen. So this is the mount, and then I have my material in it. So what I'm going to do is I'm going to run this specimen in a given direction. So let's say I'm going to run it this way. So I'm going to either have the wheel move in one direction, or I'm going to manually move my sample in that direction. So this is just movement of the specimen. All right, so what's going to happen is there's a lot of damage on the surface, but I'm applying this sample against the grit, and so there's going to be scratches, and those scratches are going to result in the direction of that specimen. So if I keep holding it, I'll get rid of all the prior damage that's much larger than this 240 grit size, and all the damage will be in that direction. So I'm removing all the damage that happens from a larger steps. So in this case, I'm removing damage from the section. All right, so I'm going to do that with running water to remove debris, and I'm holding it in a specific direction. So when all these lines go in the direction that you were moving, you want to note that time. And you note that time because we're actually going to double it. We're going to continue to grind an additional step. So let's say it takes you 2 minutes to remove all that surface. We're going to go another 2 minutes, and what that does is it removes any subsurface damage. So there may be surface damage below the surface that you can see that we want to try to get rid of. So we're going to double the time. All right, then after that, step, we're going to rinse with water. Sometimes this involves sonication to really remove those particles. And we're going to go to the next step. So our sample is again here, and let's say I want to go 320 grit. So now I'm going to put this in a direction that's different than this, right? So if I move it in the same direction, all the scratches will go in that same direction, and it'll be hard to tell when these scratches are removed. So now the typical procedure here is to rotate 90 degrees, such that now all my scratches are going to be in this direction. So this is the movement now. All right. So the reason I do this is because now if everything's moving in this direction, whenever all of my scratches align with that direction, I know that I've removed this. I can double that time and keep going to remove the subsurface damage. And then keep going through this entire process. So I'd keep going until I get to the end, or till I get a satisfactory finish on this. So you may do 400 next, same procedure, repeat it, and then 600 after that. There's many different ways of doing this. So let me just recap this for you. So 1, hold mounted specimen on lowest grit in specific direction. So we're going to move in grinding direction under water. Note the time it takes to remove prior damage. And then go for that much time more. So again, if it's 2 minutes, add 2 more minutes. All right, then I want to rinse with water. And then I'm going to rotate 90 degrees and go to next step. And I repeat. All right, so that is grinding for you. After that, we move on to polishing, and polishing is very similar to grinding. All right, like I said, we're going to move back and now go to the next step. We're going to polishing. So this is step 4 in our procedure. And like I mentioned, polishing is a continuation of grinding, and it's employed to produce a scratch-free surface. So, and with a mirror finish. So with grinding, like you just saw, we produced scratches of smaller and smaller size. Polishing is a continuation of this, just typically the mechanism is slightly different. Here we use diamond or alumina, Al2O3, a hard ceramic, and these are present in paste. So we use paste of these, and these are common ones that we have for abrasive particles. So grinding, we had grit papers with typically silicon carbide. Here we're going to have a slurry or paste that has diamond particles of a specific size or alumina particles, and we're going to place that onto a cloth. So polishing occurs by embedding these paste particles in a polishing cloth. And then the specimen is held there and polished against. So it's really similar to grinding, which is why I've included these together. The main difference is just the type of abrasive that we use. And so when we get to coarse polishing, called this because the particles are relatively large compared to fine polishing, which is coming up. We're talking about 3 to 300 microns. And there's quite a bit of overlap, as you might see from the grinding steps, because again, that 320 was about 40 microns, and so there's some overlap here with coarse polishing. And then fine polishing is around 1 micron down to 0.05 microns, which is kind of the smallest you'll ever see. All right, so we do it in the same fashion of different steps, right? We talked about increasing the grit size for grinding. We do the same thing here. We have a coarse step and a fine step until we get down to the level that we need. A couple things to note here. These polishing cloths and these paste, obviously if they get mixed up, there can be contamination. If you don't thoroughly rinse your specimen, there can be particles there that would contaminate other polishing pads. So cleaning is extremely important in these steps. And so typically the rinse that I talked about with grinding, it would be much better to sonicate. So basically put it in an ultrasonic bath to shake off those little particles and keep them from contaminating the further steps. All right, so some notes here about polishing. So again, you could do this by hand if you wanted. Most likely this is going to be a polishing wheel, the same mechanism we saw with grinding, but instead of that grit paper, we have a cloth that we put that slurry in. We typically don't press too hard. If we press too hard, we can actually form plastic deformation, so those particles can deform the top layer. So we want to avoid that, so very light pressure. And rotate it against the wheel direction can avoid what's called comet tails. So basically it's like the name implies. If you see on your surface something that looks like a comet, a particle with a tail, then those can be removed by rotating against the direction. And again, like I said, you typically want to sonicate with some type of soap to remove debris in between steps. All right, so that's polishing. And again, it's just a continuation of grinding with slightly different mechanisms. However, we can use a different type of polishing. There are different methods. This is the pretty standard, but there's also electrolytic polishing. So this is an alternative method. And it's for metallic samples. So basically, in this approach, we have our sample here that we've mounted. This serves as an anode. It's also our specimen. And this is in a electrochemical cell that has an electrolyte. So we basically put it in an electrochemical cell. It has a fluid in it, right? And this is our electrolyte. And we basically apply current, voltage, in order to have an anodic reaction with the surface. So we basically create a cathode in this system, and the surface is smoothed and brightened by this anodic reaction. So some variables that we can vary here is the bath temperature, voltage, current density in this case, and time. So we don't cause any mechanical damage. It's an electrochemical reaction from anode, electrolyte, and a cathode, which is in this machine, that causes the polishing effect. So it's a different mechanism, but it gives us the same polished mirror finish that we're after with polishing.